Thousands of years ago, well before dinosaurs walked around the world, our planet was dominated by creatures that appear to be plucked from a nightmare. Dragonflies with wings as broad as a seagull flew effortlessly through the humid skies of prehistory. Centipedes exceeding the length of a family vehicle crawled through thick, hot forests. Spiders as large as dinner plates hid among great ferns. This was not a world of fantasy. It was Earth during the Carboniferous Period, more than 300 million years ago, an era when insects attained sizes that seem incredible now. Yet, just as inexplicably as they had arrived, they vanished. What became of these ancient giants? Did a worldwide disaster eliminate them? Were they pursued by unfamiliar, frightening hunters? Or did the very atmosphere they inhaled betray them? For many years, researchers have been assembling hints hidden within rock and ancient wings. Historic enigma uncovering how delicate the balance of life truly is. Join us as we travel back in time to explore one of Earth's greatest biological enigmas. What truly led to the extinction of the giant insects? Approximately 300 million years ago, well before dinosaurs or mammals emerged, the Earth was a realm similar to what we recognize today. Vast, moist, and covered in limitless vegetation. Majestic tree ferns, club mosses, and horsetail species created dense jungles stretching from one horizon to the next. Enormous floods and swamps inundated large portions of the terrain, nourishing rivers laden with rotting material, the same floods that would eventually form the coal deposits we extract today. The air was heavy, rich, and almost suffocating, containing as much as 35% oxygen, far higher than today's 21%. Lightning storms crackled more fiercely, wildfires burned brighter, and this oxygen-rich world created the perfect conditions for something extraordinary: insects of unbelievable size. High above the woodlands, enormous dragonflies such as Meganeura dominated the air, their wings spanning nearly 70 centimeters, broader than a human arm can extend. On the forest floor, gigantic millipedes like Arthropleura moved through the vegetation, with some reaching lengths over 5 meters. The humming, moving, and darting of existence permeated every part of this ancient planet. It was an ecosystem dominated not by mammals or reptiles, but by arthropods, beings shielded in armor and fueled by air. At that time, there were no birds, no bats, and no flying reptiles to compete with them. The insects completely owned the skies. It was the golden age of arthropods, an era when evolution appeared to challenge the boundaries of life itself. However, this age-old paradise would not endure indefinitely. Beneath the Earth's surface, continents were moving, climates were altering, and new predators were starting to appear. Gradually, nearly unnoticed, the equilibrium that enabled these giants to flourish started to shift. What precisely enabled this world to exist, and what led to its downfall? To answer that, we must first understand the science behind their size and the invisible force that once filled their lungs: the air itself. The age of giant insects. The tale of Earth's enormous insects fundamentally revolves around air, the unseen factor that influences every living breath. In the Carboniferous Period, approximately 359 to 299 million years ago, the atmosphere was significantly unlike the air we inhale today. Researchers examining bubbles of ancient air enclosed in rocks and chemical indicators within sediments have found that oxygen levels at that time were remarkably elevated, reaching as much as 35%, in contrast to the current 21%. That variation may not seem significant, but it transformed everything. Higher oxygen meant that animals relying on simple air diffusion, like insects, could grow far larger than their modern descendants. You see, insects don't breathe through lungs like we do. Their bodies are equipped with a network of tiny tubes called tracheae, which carry oxygen directly to their tissues. This system works efficiently only across small distances. In today's atmosphere, that's why insects remain relatively small. If they grow too big, oxygen can't reach the innermost parts of their bodies fast enough to keep them alive. But in the Carboniferous world, the air itself carried more oxygen per breath. That meant the tracheal system could supply much larger bodies. Essentially, the environment functioned as a biological enhancer, enabling insects to grow to tremendous sizes without experiencing suffocation. The outcome was a planet alive with titans. The skies were ruled by Meganeura, a dragonfly-like hunter with graceful but strong wings nearly 70 centimeters wide. It preyed on lesser insects and possibly early amphibians near riverbanks. On the forest floor, the enormous millipede Arthropleura, measuring over 2 meters long, consumed decomposing vegetation in the wet soil. Fossilized footprints of this organism, discovered in Scotland and Germany, indicate that it could readily compete with a small crocodile in size. During the floods, ancestral forms of cockroaches, crickets, and beetles prospered. Some carried intricate wings and bodies armored with natural plating, adaptations to the humid, oxygen-rich jungles that defined this age. The lack of competition among vertebrates also had an important impact. There were no birds, bats, or flying reptiles present at that time. In the air, insects faced no competition. They faced no predators capable of pursuing them in the air, nor any species vying for their ecological role. This evolutionary flexibility enabled them to explore, growing bigger, quicker, and more varied with every million years that went by. The climate itself also supported their governance. Warm, humid, and consistent for millions of years, it nurtured thick plant life that generated significant quantities of oxygen via photosynthesis. The shallow seas and marshy forests of Earth functioned as a huge carbon sponge, capturing carbon dioxide and creating a world abundant in oxygen and low in carbon, ideal for enormous arthropods. This was, quite literally, a planet breathing deeply, fueling life to extraordinary extremes. For millions of years, this equilibrium remained constant. Insects developed, adjusted, and expanded into all areas of the Earth. Fossils from this period reveal wing patterns, body structures, and even preserved impressions of their intricate tracheal systems, mute evidence of a world that once buzzed with immense life. However, this golden balance was delicate. The climate of Earth is always changing, and far below the surface, tectonic movements were merging the continents into a giant supercontinent, Pangaea. This gradual change started to dehydrate the abundant Carboniferous wetlands. As forests declined, oxygen levels began to fall. The very air that had once made giants possible was beginning to change, setting in motion the slow, inevitable downfall of these prehistoric titans. The mystery begins, the mass decline. For almost 60 million years, the era of enormous insects flourished, but even the strongest periods in Earth's past ultimately conclude. Approximately 275 million years ago, as the Carboniferous period transitioned into the Permian, a transformation started to occur. Gradually, but undeniably, the circumstances that enabled these massive beings to rule the Earth began to disintegrate. Geological and fossil records convey a distinct narrative. The dense, marshy woodlands that previously covered the continents started to disappear. Enormous geological movements united almost all land areas into one supercontinent, Pangaea. As the continents came together, the climate of Earth changed. Extensive areas that were formerly moist marshlands became arid and periodic. The worldwide environment became increasingly unstable as severe droughts and wildfires occurred more often, and with the collapse of those ancient forests came a crucial loss: oxygen. As vegetation decreased, so did the planet's oxygen production. By the late Permian, atmospheric oxygen levels had dropped from their Carboniferous highs of about 35% to nearly 21%, roughly what we breathe today. That reduction may not seem catastrophic for most life, but for insects, whose bodies depend on direct oxygen diffusion, it was devastating. The larger the insect, the harder it became to deliver enough oxygen to its inner tissues. Fossil evidence from this time shows a distinct pattern. Insect species that previously achieved remarkable sizes diminished in size. By the end of the Permian, the enormous dragonflies and giant millipedes had nearly vanished. However, decreasing oxygen was not the sole difficulty. Novel life forms were emerging. Amphibians and primitive reptiles were quickly dispersing throughout the terrain, adjusting to both aquatic and arid environments. These recent predators and rivals intensified the strain on an ecosystem that was already stressed. In this evolving world, being small has turned into an advantage. Smaller insects needed less oxygen, bred more quickly, and could adjust more readily to changing environments. Evolution started to prioritize agility instead of size and resilience over power. Thus, gradually, the ancient titans disappeared from the fossil record, leaving only remnants of wings, signs of exoskeletons, and subtle imprints in stone. The era of giants was coming to a close, yet for scientists, the query persisted. What precisely led to their deaths? Was it really the air or something much more intricate? Theories. What really killed the giant insects? For decades, scientists have searched for the answer to one of prehistory's most fascinating questions. What really killed the giant insects? At first glance, the cause might seem simple, a drop in oxygen levels. But as researchers dug deeper, they uncovered a far more complex story, one shaped by multiple forces working together to end the reign of these ancient giants. Let's explore the leading theories, each offering a vital piece of the puzzle. Theory 1. The oxygen collapse. The most widely accepted explanation begins in the air itself. During the Carboniferous Period, oxygen levels peaked at around 35%, the highest concentration in Earth's history. By the late Permian, that number had plunged to roughly 21%, a drop of nearly 40%. For most animals, such a decline might have been manageable, but not for insects. Their unique breathing system depends entirely on passive diffusion through microscopic tubes called tracheae. These tubes have no lungs or muscles to pull air in. Oxygen simply travels along a gradient from the outside environment into the insect's body. This works efficiently when the air is oxygen-rich, but when oxygen falls, the diffusion process becomes slower and less effective. For small insects, that's a minor inconvenience. For larger ones, it's fatal. Their internal tissues simply couldn't get enough oxygen to survive. To confirm this theory, scientists have conducted controlled laboratory experiments. In one study, researchers raised modern dragonfly larvae in chambers containing elevated oxygen levels, mimicking Carboniferous conditions. The results were remarkable. The dragonflies grew significantly larger than normal, suggesting a clear link between oxygen concentration and insect size. This experiment supports the idea that giant insects were a direct product of Earth's high oxygen atmosphere, and when that atmosphere changed, evolution forced them to shrink or perish. But oxygen alone may not tell the whole story. Theory 2. The rise of the vertebrate sky hunters. As the Permian period unfolded, a new type of creature took to the skies, vertebrates. By around 260 million years ago, early amphibians, reptiles, and eventually pterosaurs were evolving into more efficient predators. The appearance of these vertebrate flyers and later birds in the Mesozoic era completely transformed aerial ecosystems. For the first time in history, insects faced serious competition and serious threats in the air. Giant insects like Meganeura may have ruled unchallenged for millions of years, but their large size suddenly became a disadvantage. They were slower, easier to spot, and less agile than smaller insects. Evolution responded accordingly. Over time, natural selection began favoring smaller, faster, and more maneuverable insects that could outfly, outbreed, and outsmart the new wave of predators. In this view, the fall of the giants wasn't caused by a single environmental collapse, but by an evolutionary arms race, one that insects ultimately survived by becoming small. Theory 3. Climate shifts and habitat loss. The late Carboniferous and early Permian weren't just times of biological change, they were also marked by massive climatic upheaval. As the continents merged into Pangaea, the planet's climate patterns changed drastically. Global temperatures fluctuated more wildly. Rainfall became uneven. The once lush tropical floods that produced abundant oxygen began to dry out, replaced by arid deserts and seasonal forests. Fossilized plant records show that dense, oxygen-producing lycopsid trees, which once dominated the landscape, declined sharply during this time. As they disappeared, oxygen production fell, and with it, the ecosystems that supported giant arthropods. This environmental shift also altered the food chain. The detritus-rich floods that fed enormous decomposers like Arthropleura were replaced by dry, mineral-poor soils. Simply put, there wasn't enough food or moisture to sustain such massive plant-eating arthropods. The climate theory explains not only why these insects vanished, but why they never returned. Once the world dried out and oxygen stabilized at lower levels, the ecological niche for giant insects simply ceased to exist. Theory 4. Evolutionary competition and adaptation. While oxygen and climate clearly played major roles, evolution itself may have sealed the fate of the insect giants. Smaller species tend to reproduce faster and adapt more quickly to environmental stress. When conditions changed, whether through falling oxygen, new predators, or shrinking habitats, smaller-bodied insects had the advantage. They could evolve in response to new challenges within a few generations. Larger species, however, were locked into slower reproductive cycles and specialized ecological roles. As conditions deteriorated, these giants could not adapt fast enough. This process is known as selective pressure that gradually filtered out the large species, leaving behind only the smaller, more efficient survivors. In the end, the shrinking of insects wasn't a single event, but a gradual evolutionary response to multiple overlapping pressures. Theory 5: Catastrophe and the Great Dying. Ultimately, the context includes one of the planet's most catastrophic events, the Permian-Triassic extinction, which occurred around 252 million years ago, often referred to as the Great Dying. It eliminated approximately 90% of ocean species and 70% of terrestrial species. The cause remains disputed. Colossal volcanic eruptions in Siberia, methane release, ocean anoxia, yet the consequences were disastrous. Even if the enormous insects had made it this far, the ecological turmoil of the Permian extinction would have done them in. Significant changes in temperature, oxygen depletion, and habitat loss generated conditions too severe for large arthropods to survive. Following this event, the fossil record indicates that insect body sizes never returned to their maximum levels from the Carboniferous period. The era that had previously favored giants was lost permanently. So, what really killed the giant insects? The evidence suggests not one culprit, but a series of interconnected reactions. Initially, declining oxygen levels rendered large body sizes unfeasible. New predators and competitors emerged, compelling insects to adapt or face extinction. In the meantime, changing climates and vanishing forests obliterated the stable, oxygen-filled environments they relied upon. Ultimately, the worldwide catastrophe of the Permian extinction wiped out any remaining survivors. It wasn't a single factor. It was an ideal combination of environmental and evolutionary shifts. The decline of the massive insects serves as a reminder that even the most powerful beings are connected to the fragile equilibrium of Earth's systems. When that equilibrium shatters, evolution alters the guidelines. Scientific evidence and experiments. For centuries, the notion of enormous prehistoric insects appeared nearly legendary, the realm of creativity and fantasy. However, as time passed, evidence started to surface, one fossil after another, illustrating a clear image of the Carboniferous environment and validating the reality of these massive beings. Fossils that tell the story. In the late 19th century, miners digging in the coal seams of northern France unearthed something extraordinary: the fossilized wings of a dragonfly-like insect, nearly 70 centimeters across. It was named Meganeura monnier, and its discovery stunned scientists. For decades, it held the record as the largest known flying insect in Earth's history. Similar discoveries followed. Paleontologists discovered fossilized trackways of a giant millipede in Scotland and Germany, which was subsequently recognized as Arthropleura armata. Certain tracks extended over 2.5 meters, suggesting a creature comparable in size to a human. These fossils served not only as evidence of life, they were glimpses into a forgotten world, encapsulated in rock. What confused scientists, however, was why these beings went extinct. Fossils indicated that following the late Carboniferous, insect sizes started to decrease significantly. The pattern was evident, but the reason required validation, and that's where contemporary science intervened, recreating the ancient atmosphere. In the early 2000s, a group of scientists at Arizona State University performed a pioneering experiment. They cultivated contemporary insects, beetles, crickets, and dragonflies in uniquely constructed chambers with oxygen concentrations varying from the present 21% to up to 35%, replicating the environment of the Carboniferous era. The outcomes were remarkable. Under high oxygen conditions, the insects increased in size and accelerated in their development. Dragonflies flies nurtured in 30% oxygen developed up to 20% bigger than those in standard air. This experiment yielded strong, tangible proof that atmospheric oxygen directly influences insect growth, confirming years of theoretical understanding. Further experiments by entomologists like Alexander Kaiser and John Vandenbroeks revealed similar patterns. The structure of an insect's tracheal system, those microscopic breathing tubes, actually scales differently under varying oxygen conditions. In higher oxygen environments, insects need smaller tracheae, freeing up space in the body for muscle and tissue growth. But when oxygen drops, those tubes must expand to bring in enough air, limiting the insect's maximum possible size. This means the Carboniferous atmosphere didn't just allow giant insects, it engineered them, oxygen levels, and the geological record. But how can scientists determine what ancient oxygen levels were initially? The solution is hidden within geological proxies, chemical indicators embedded in rocks and fossils. Researchers analyzed the proportions of carbon and sulfur isotopes in sediment layers and the oxidation states of ancient iron minerals to deduce historical atmospheric oxygen levels. These techniques consistently reveal a significant increase in oxygen during the Carboniferous, succeeded by a gradual decrease throughout the Permian. The correlation becomes clear when the oxygen curve is compared to the fossil record of insect sizes. As oxygen rises, insects grow larger. When it falls, their maximum size collapses. It's one of the clearest cause and effect relationships in paleobiology: predators, pressure, and adaptation. Fossil evidence also supports the theory of predatory pressure. In rock layers corresponding to the late Permian and Triassic periods, scientists have found fossils of early flying vertebrate reptiles that would eventually give rise to pterosaurs. Around the same time, insect fossils became smaller and more agile, suggesting that evolutionary pressure favored flight maneuverability over size. Computer simulations of insect flight dynamics further support this. Models show that while large wings provide lift, they reduce turning speed and acceleration, crucial traits when escaping predators. Smaller insects, therefore, had a survival advantage in the newly competitive skies. Piecing together the puzzle. Taken together, these findings reveal a clear and compelling story. Fossil findings unequivocally establish that enormous insects dominated the skies and forests of Earth, and geochemical data demonstrates that atmospheric oxygen levels in the Carboniferous period were significantly greater than those of today. Laboratory tests indicate that oxygen-rich environments directly support the growth of larger insects, while evolutionary research clarifies how emerging predators and changes in ancient ecosystems ultimately led to the extinction of these giant species. What used to appear as an ancient puzzle has transformed into a scientifically substantiated account of cause and consequence, a tale in which atmosphere, evolution, and surroundings collaborated to influence the course of life. To genuinely grasp why the era of giants concluded permanently, researchers now think it was not one cause, but an amalgamation of various factors. An ideal tempest of decreasing oxygen, shifting climates, and increasing predators that traversed the globe and altered the trajectory of evolution itself. The multi-cause theory. By the end of the Permian, the tale of Earth's enormous insects had reached its intense peak. Fossils, laboratory studies, and geological evidence all indicate one undeniable fact: no solitary antagonist brought about the downfall of these gigantic beings. Rather, it was an ideal convergence of interrelated factors, each enhancing the others, that transformed life on Earth. Initially, there existed the atmosphere itself. As oxygen concentrations fell from their Carboniferous high of 35% to the Permian average of about 21%, the tracheal respiration systems of large insects lost efficiency. Insects with larger bodies faced challenges in supplying sufficient oxygen to their tissues, whereas smaller insects thrived in this less dense air. The very environment that had supported their massive growth was now working against them. Secondly, the emergence of new predators created evolutionary stress. Primitive amphibians, reptiles, and later the initial flying vertebrates started to inhabit the skies and woodlands. Colossal insects, previously invincible in the air, now encountered swift predators. Natural selection preferred smaller, quicker, and more agile species, organisms that could evade dangers and reproduce rapidly. Third, alterations in climate and habitat were significant factors. The formation of Pangaea led to significant changes in precipitation and temperature, slowly desiccating the verdant, marshy woodlands. Food supplies for herbivorous giants like Arthroplura decreased as oxygen-generating plants diminished, which further reduced atmospheric oxygen levels. Ultimately, the devastating Permian-Triassic extinction, occurring 252 million years ago, struck a decisive blow. Severe volcanic eruptions, climatic disturbances, and ecological disintegration exterminated the majority of large species, permitting smaller, adaptable insects to take over the Earth. The outcome: an entire overhaul of insect existence. The massive creatures that once dominated the skies and forests disappeared from the fossil record, leaving behind only smaller, more adept descendants. Ultimately, the decline of the massive insects was not due to a singular catastrophe, but rather the interaction of several factors: oxygen depletion, predation, habitat destruction, and mass extinction working simultaneously over millions of years. It was a lesson from ancient times. In nature, even the strongest beings are tied to the delicate equilibrium of their surroundings, and when that equilibrium changes, evolution transforms life in ways that are both striking and permanent. Modern connection: could giant insects return? Although the giants of the Carboniferous are no longer present, their tale still captivates both researchers and the general public. It poses an intriguing question: might massive insects make a comeback? The concise response, as per contemporary science, is no. At least not on the Earth we have today. The atmosphere of the planet has altered significantly. Oxygen concentrations hover near 21%, significantly less than the 35% that previously supported the growth of organisms such as Meganeura and Arthroplura. Modern insects are limited by the same tracheal breathing system. Without elevated oxygen levels, their bodies can't grow to those ancient dimensions. Even if oxygen were to rise, other elements would hinder a genuine comeback of the giants. Contemporary ecosystems are increasingly intricate, featuring birds, bats, and various other aerial predators. Habitats capable of sustaining large insects, thick, wet deluges enveloping whole continents are gone. Evolution has enhanced insects for speed, maneuverability, and reproductive success instead of mere size. Still, the story of giant insects remains a valuable source of knowledge for science. Laboratory tests mimicking ancient oxygen conditions allow researchers to investigate the interaction between physiology, environment, and evolution. These investigations improve our comprehension of how life adapts to changing environments, a topic increasingly significant as people alter our planet's climate and oxygen dynamics. In a way, the giants endure, not in size, but in the biological discoveries they reveal. Their rise and fall remind us that life is deeply connected to its environment, and even those who seem unbeatable can be affected by the subtle shifts in air, water, and soil. Outro. The narrative of Earth's massive insects is not just a story of dimensions and wonder, it is a tale of equilibrium, adjustment, and the delicate strand that supports existence. Eons ago, dragonflies bigger than seagulls flew through the skies, and millipedes as long as cars crawled across the forest floors. For a period, they were invincible, a proof of the influence of evolution and the life-sustaining energy of oxygen. However, the world shifted. The atmosphere became sparse, hunters appeared, woodlands withered, and disaster hit. One by one, the giants vanished, leaving only fossils, traces, and the subtle marks of a vanished world. Today, we examine these remnants not only to appreciate their scale, but to comprehend the intricate relationship between life and surroundings, a balance that even the strongest species must acknowledge. So the next time you spot a dragonfly darting over a pond, recall that its small frame holds the heritage of giants, a murmur from a time long past when the heavens were dominated by creatures of the sky. Though the giants may never come back, their tale lives on, an ancient enigma unraveled by science, yet still able to fascinate us.